We have so far looked at Boolean functions. We have viewed the family of all Boolean functions as a vector space, and therefore, each Boolean function is a vector. Similarly, we looked at periodic functions, and we noticed that discrete periodic functions can be viewed as vectors. And in each of these cases, we defined an appropriate Fourier basis or Fourier spectrum. So, we are now going to look at how to transform a vector from the standard basis to the Fourier basis. This transformation is quite naturally called Fourier transform. And in particular, we will look at the fast Fourier transform algorithm, which is an efficient way to perform this transformation, and it will be applicable in some contexts, but not in all contexts. So, let us recall a Fourier spectrum of a vector is its representation in the alternative Fourier basis. And since this is a change, this is viewed as can be viewed as a change of basis, we can perform this transformation by a suitable transformation matrix multiplication. So, the Fourier transform therefore, is just any algorithm to transform a vector from its standard basis to its Fourier basis. The matrix multiplication version being the so-called brute force way to perform this transformation. So, this transformation can be viewed as taking a vector in the standard basis and multiplying the transformation matrix with that vector in order to get the vector in the Fourier basis. If these vectors are of some dimension say d, then the time it will take to perform this transformation for a single vector is O of dimension squared. So, a natural question would be, can we do better? Can we devise an algorithm that will run faster than d squared time? And in some cases, in particular we notice this in discrete periodic functions and therefore, the discrete Fourier transforms that can be applied to discrete periodic functions. We will notice that this transformation matrix has some structure. In particular, the terms in each row will be in geometric progression. Moreover, the entries can also go into the complex domain, and we will exploit these properties to devise an O of d log d time Fourier transformation algorithm. And this algorithm is called the fast Fourier transform algorithm because it is faster than the brute force d squared time algorithm. This is an example of a divide and conquer paradigm of algorithm design. As it turns out, this algorithm is applicable to other Fourier transforms, not just discrete periodic functions. In particular, it is quite suitable in the context of polynomials. We will describe this algorithm, the fast Fourier transform algorithm, in the context of polynomials, for which we will first show that polynomials themselves can be represented as vectors in a suitable vector space. We will define a suitable alternative basis, and the transformation to that alternative basis will be performed using the fast Fourier transform algorithm. So, this will be a good case study under which we can understand the fast Fourier transform algorithm. And then we will see how this exact same algorithm can be applied to polynomials. It can also be applied to discrete periodic functions and therefore signal processing and things like that. So, a quick rundown of the various vector spaces that we will be considering. Well, we considered Boolean functions, we considered discrete periodic functions and polynomials. Recall that our exposition of the fast Fourier transform algorithm, that is one way to transform a vector from its standard basis to the appropriate Fourier basis, will actually be explained in the context of polynomials. And then we will show that the fast Fourier transform algorithm is also applicable in the context of discrete periodic functions. Now focus on why we need the Fourier basis. What do we gain by transforming a vector from the standard basis to the Fourier basis? Many signals in vectors in real world contexts are often dense in the standard basis. Their standard representation will have a lot of non-zero terms and may look pretty complicated. But oftentimes, once they are transformed into the appropriate Fourier basis, we will notice that there will be a few prominent terms and the other terms will not be prominent. They will either be very close to 0 or completely zeroed out. And so, a lot of real world signals and vectors are actually sparse in the Fourier basis. So, if we want a more compact representation of real world signals, it would be helpful to have transformed them into the appropriate Fourier basis and then process them in that compact form. Let us look at one such example, which really illustrates this notion of sparsity. Here is an example of a periodic function, and as you can see, this periodic function appears quite complicated. And if you were to sample this periodic function in discrete points in time, the very few terms will be 0, most of the terms will be non-zero. Let us now look at this same periodic function after we transform it into the Fourier spectrum. And we will see, we will progressively include an increasing number of terms from the Fourier spectrum to see how well the first few terms approximate this function. Well, when we use one sine wave, this is the approximation we get. Of course, this is not very good, but let us add a few more sine terms. Now, with 4 sine terms, we are able to approximate this function quite well. With 5, even better. And if we add a few more, in particular in this example, we have shown the Fourier spectrum representation of this periodic function using 25, the first 25 sine waves. Notice that we are able to get a pretty accurate approximation of the original periodic function. So, this function, even though it may appear very complicated in the time domain, depending on the level of approximation we need, we could appropriately approximate it in the frequency domain. Let us now look at a second application of Fourier transforms. Oftentimes, a vector in its standard basis may not be suitable for some operations. We may need to convert or transform that vector into some suitable alternative basis before it can be made convenient. And we see one such example when we encounter polynomial multiplications. Typically, if you want to multiply 2 polynomials of degree d, we will require O of d squared time. Suppose these 2 polynomials have been evaluated at several points. In particular, we will go on to show that d plus 1 points is sufficient, then it is easy to obtain the product polynomials. So, if we have evaluated it at d plus 1 points, then we can simply multiply the two polynomials pointwise. So, in O of d time, we can obtain the product polynomial, and therefore, there is hope of performing polynomial multiplications faster, provided we can actually convert a polynomial representation from its usual form to this point value representation, basically evaluations at several points. However, if we want to evaluate a polynomial at d points, that itself might take theta of d squared time. However, if we carefully choose the points, the set of points at which we evaluate the polynomials, and this will go into the complex domain, we will explain in detail in the next lecture that this is actually a Fourier transform, and this Fourier transform can be performed in O of d log d time. So, we will show that polynomials of degree d can be viewed as vector space of dimension d plus 1. Such a polynomial can be evaluated at d plus 1 distinct points, and this evaluation we will need to show is essentially a change of basis, in particular change of basis into what is called the Lagrange basis, which we will explain in the next lecture. We will present the fast Fourier transform algorithm as the transformation from the technique from the standard basis to this particular Lagrange basis. This transformation will take O of d log d time. This in this transformed basis, the polynomial is essentially represented as its evaluation in d plus 1 points. So, now we take two polynomials evaluated into the appropriate Lagrange basis. Now, we have these two polynomials represented based on their evaluations at d plus 1 points. So, if we want to multiply them, all we really need to do is multiply them pointwise, and we will get the product polynomial in O of d time. Of course, we will also, once we get the product polynomial, it will unfortunately be in the Lagrange basis, because we will be multiplying the two polynomials in the Lagrange basis. So, in getting the product also in the Lagrange basis, we will have to find a way to return back to the standard basis. And as it turns out, this transformation back to the standard basis is also an application of the fast Fourier transform algorithm. So, this entire process of taking a polynomial in the standard basis, converting it to the appropriate Lagrange basis, multiplying two such polynomials that have been converted to the Lagrange basis, and then returning back to the standard basis, all of this can be performed in O of d log d time. And we will describe this process in detail, and we will use this context to explain the fast Fourier transform algorithm. Finally, we will end with a description of how this algorithm can be applied in the context of signals and periodic functions, in particular discrete periodic functions. Thank you.